to restart again. Excellent, thank you.
So that was a good point. Now, these two things need to be the same. Okay, so for instance, you have a puddle. You got a puddle, young puddle. Now, does the atmospheric pressure push down or push up?
Down.
Push down, right? It's the atmosphere. And there's a few scenarios of what happens, right? Technically, if atmospheric pressure is winning and vapor pressure does nothing, it's going to look like a puddle of water. If the atmospheric pressure is winning that much, it's going to look like a puddle, right? It's not allowed to become a gas. I'm pushing it, literally the air is pushing on the water so much it can't do anything but be a liquid. I can't separate, I can't get my molecules far apart because I'm being oppressed, I'm being pushed down. It literally is pushing down on it. The next one. The next one is when they're tied. When they are tied, the second they are tied, the literal moment, that means that the water is making enough vapor to literally fight the atmospheric pressure. So the water vapor is fighting all those oxygen molecules, all those nitrogen molecules that are there. And what you'll start to see is, right, bubbles are going to start to form. And bubbles are going to form because bubbles are full of gas, right? We know that. And that's because as the vapor pressure is starting to push through, those bubbles are going to be able to pop and break the surface. Here they can't break the surface. The atmosphere is pushing them right down. I want to be a gas, I want to be a gas. No. But if they get stronger, this is where bubbles start to occur. This is where boiling starts. Essentially, yeah, they're fighting. And then under this scenario, right, if the vapor pressure is super strong and the atmospheric pressure is not.
That's crazy. You can remember that because boiling point is when you start fighting.
Essentially, yeah. And it boils over, right?
Yeah.
That's literally where that saying came from. In here, you're going to have bubbles. This is straight boiling. You're going to have bubbles, and more importantly, you're going to see the vapor. Because the vapor is the vapor pressure pushing up. You literally see that coming from the pot, from the puddle, from anything. You will see the vapors. But I'm going to be honest with you. I didn't answer this question at all. This has nothing to do with this. Okay, this is just the basic. Okay, that's the basics of it. So if you know a boiling point, you don't know how to apply it to vapor pressure. But vapor pressure is the key. Here's what happens, right? When you have, that was a necessary rabbit hole, trust me. You might remember me doing this. If you have two different things. If this is pure water, it's going to have a vapor pressure and it's going to be A-okay. We'll say 0.8 atm, that's the vapor pressure. But what will end up happening is if you have salt water, again, I'm just literally drawing things blocking the water. What happens is vapor can't become as easy. Essentially, the salt particles are blocking the water vapor from forming. Because again, in order for that vapor to go up to the surface, it's got to make its way all the way to the top, and then it's okay. But if it keeps hitting salt particles, like, I'm trying to go up, I'm trying to go up, it's like, those of you that, we talked about World War II, right? Depth charges, mines, stuff like that they used during World War II on the Pacific. Can you swim up as easy if there's a mine right in front of you? No, you got to go around the mine. And that's going to, one, slow you down, and two, some people are going to hit the mine. Some of those particles of gas end up hitting, the salt particles, and nothing happens. So this one, when it vapors, these particles are literally everywhere, and some particles spread out everywhere. And the vapor pressure, maybe it'll only be 0.4 atm. And it's literally because particles are blocking that gas from forming. Imagine how much harder you have to work if half the things in your water are trying to stop you. You know? Imagine like Ashley trying to come up to the front of the class, right? No one is stopping her. Ashley's just allowed to go to the front of the class. The second she hits here, she's a gas and she can do whatever she wants. But imagine if I told half of you that you're salt particles and you're trying to block her. Now Ashley might have to go around desks and go around, and people still might try to stop her. She might not become a gas. I'm sorry, Ashley. But that literally is kind of how it works. Especially if she's all the way, because this is the front of the beaker and that's the bottom of the beaker. You've got to work your way through all of this. That might take you a while. And because of that, the vapor pressure will go down. There's not as much gas. There it is. And again, why does this impact this? If you're not making as much of this vapor, you're not going to boil, right? You have to reach the atmospheric pressure. So for boiling point to work, if you have salt water, you're going to need a lot more energy to get this up from 0.4, maybe back up to 0.8 like the air. The air is roughly 1. If you're 0.4, you've got a long way to go. You need a lot more energy to do this. And more energy, higher temperature. So now the particles need to move even faster to blast their way through. If Ashley gets a running start, and Vermin and Jose are holding their arms out, if Ashley's walking, she's not going to get through that. But if she's running, she might. Red Rover.
Would a good way to answer why the boil point increases would it be because particles at a block the gas process coming up?
That would be perfect for this one. That'd be perfect for this
But
one.
do you
For boiling.
Do you use number 2 to describe number 1? Though?
Yes, you will need that. Okay.
So how would you?
What would I expect to see from boiling point at the
Yeah.
very least?
Yeah.
I would expect that you should be able to say, because the vapor pressure isn't being produced as much, or something along those lines, what I would expect to hear is something like this. As the vapor pressure goes down, you need more energy to eventually equal the atmospheric pressure, which is when it boils. Again, how am I going to get more vapor pressure? You heat it up. Right? If you want water to boil, you heat it up. It's that kind of philosophy. So I would ask for at least that. Because do I understand? Are you going to talk about like this perfectly at the atomic level and then this perfectly at the atomic level? Probably not on the final, right? You have a lot of other things going through your mind, and I understand that. And I know that this is one thing. But if you're giving me at least the vapor pressure is lower when I add salt, because things are blocking it, it's not able to become gas as easily, you're going to need more energy to get that atmospheric pressure to go up. Again, as temperature goes up, pressure goes up. Gay-Lussac. And you need more energy to reach the boiling point. That's why the energy goes higher, higher boiling point. So it is very step by step. But again, I also understand that this is one thing. Yes?
Okay, so the boiling point increases because you need more energy to produce the vapor pressure to make the atmospheric pressure at which it boils.
To meet the atmospheric pressure. Then yes. Because you're not going to change the atmosphere, right? Right? Because if I have a Bunsen burner and I'm holding it in the air like this, is the air really going to heat up? You think one Bunsen burner could heat the whole room?
To meet the atmospheric pressure?
Yeah, because atmospheric pressure isn't going to change. That's a constant. Right? It's always pushing down on you guys. 14.7 pounds per square inch. And again, really the backbone is this one. Because the third one, about freezing point, is this. I don't want to word this. I'll do this. So with this one,
Oh, I get it.
so the good news is this one's the easy one. Okay, this is the one that you all did really, really well on the test. The particles, the new ones, right? The things that you were adding to your pure solution. Those literally get in the way and block the other particles from getting closer together. Very similar to what salt water is doing with vapor pressure. It does it with freezing, right? For you to freeze, your particles, again, solids are close together, liquids are not. So for you to freeze, you gotta get your particles close together, increase the IMFs. Well, freezing literally blocks those IMFs from forming, essentially, meaning you need to get it even colder and even closer. The salt literally is blocking. So again, another thing where you can literally say those particles are in the way and blocking. So for example, remember we're playing the game of dots? If there's no salt, everything is able to form, and you have ice, bacon. No, I'm just kidding. No big deal, right? Everything is cool. Okay? Freezing point, 0 degrees. Here though, if I add, I'm just going to add 2 atoms of salt. So that's going to be 1, no, I'm going to add 1 Na plus, 1 Na plus. I'm just adding 2 atoms, that's it. Cl minus, Cl minus, random. One ice. The salt blocks it. And again, because salt has a Van Hoff factor of 2, it's going to have a pretty good effect. So here, again, to you really get water to freeze, you need to get it to be closer and closer together. So instead of the freezing point, will this be H2O, this is salt, H2O. This one might be again -5 degrees. Because now you need to get it even colder, take away even more heat, and eventually the particles will get close enough together where they can like wrap around it. But as is at 0, not enough energy. Yeah. But eventually, if you get these 2, is that me and you? No. Why am I? Well, I did that in class. So yeah, but eventually, if you get these 2 girls close enough together, could they be able to go around? Right? Yeah, absolutely. And again, that's the why. That's the why. And that, again, just to let you know, that was the #1 thing your class asked about, #3 overall. How are we looking at time? What's that time? 14. Excellent. Excellent. I probably have time for one other thing. Are there any questions on this? Now, also, I want you to keep in mind something very, very special about this final, which I'm doing for you guys, okay? This question, you know there's going to be something on the final with Kilgore properties, right? You know it. Can we agree on this? You are intelligent. You know there is something somewhere. You don't know where it is. I could give you the math of it, That might be it. I could give you the math and free response. I could just give you the free response. I could give you multiple choice. I could do a whole bunch of things. But you know you're going to see something with it. On the math and short answer, do you have to answer everything?
No.
Do you have to answer everything?
No.
No. Right. So again, if you're looking at this, and that's a really beautiful thing about this day. If you are looking at this right now and you're like, there is no way I'm going to be able to explain this, skip it. Don't do it. It happens. There's no punishment. Okay? Just make sure you're that much better on everything else. Okay? Again, as a reminder, how much extra credit could you get on the final?
2%.
Someone said it. It's 8. Right? So, again, if this isn't the one you want to try, don't try it. If, depending where it is. Okay? Use that information to your advantage, all right? Anything else? Or are you fried for today? Fried for today? All right, cool. We'll pause there. We'll pause there. I have presents for you. This is your quizzes, which tells you the extra credit you got back for the test. This is all in the grade book. And there's a few other late things in here. I didn't get all of it in, but I got most of it. You want to help pass it out?